Welcome again to another lecture in the deep learning tutorial series. In this lecture, we'll be focusing on gradient descent algorithm. The gradient descent algorithm is a very important algorithm in the deep learning, in training the deep neural networks. In the sense that for us to be able to uh, identify the set of weights and biases that will fit our training data, that will fit our model, that will be the best for our model. We need to be able to do what we call the backpropagation and update the weight that have been initially randomly initialized so that they can be updated appropriately to the set of weights and biases that is the best for the model in question. So the gradient descent algorithm helps us to be able to perform these tasks. And the algorithm is very simple and intuitive. Now what it says is you continue to do this until it converges. And what is that? You take the partial derivative of your total error. If you watch in one of our previous tutorials, you will discover we mentioned how we estimate the total error of the forward propagation. That is, we measure how good is our model from the actual predictions. So after getting the total error, we need to do a partial derivative of the total error with respect to each individual weight in our network. The reason why this is, when you do the derivative of a straight line, it gives us an intuition of in what direction to move in order to get to the local minimum. I'm sure you must have seen it in some literature where if you have a particular drawing this way and you are actually here, you're actually in this location, you can do a derivative of this point to be able to know the direction of the slope, and essentially you move in the negative direction of the slope in order to be able to get to the global minimum. So in this case, what we are having here, we're taking a simple example. Say for instance, we have just the bias and just one weight, W0 and W1. So what we do, you take a partial derivative of the error with respect to the first weight, which is W0. And once you get that value, you multiply it by the learning rate, which is alpha. Alpha, the learning rate, tells us how big our steps towards the direction of the global minimum. So the number of steps, how big the steps that we take towards the global minimum. And we subtract the current weight, which is W0, from this value and update it to the new values. We do the same for the second weight, which is W1. Do the partial derivative with respect to W1, partial derivative of the total error. You will see here that this contains the entire error with respect to W1 multiplied by alpha, and we subtract from W1 the current one and replace it with the new value. This alpha can be fixed, or it can be what we call an adaptive learning rate. An adaptive learning rate, you see that in a number of optimizers which we'll look at excuse me, which we'll look at in subsequent series. But essentially what it's saying is when we have an adaptive learning rate, it means that our learning rates keep changing as we move from certain number of steps, or what you call epochs, to another, so that we can systematically move towards the direction of the global minimum, taking larger steps initially and taking smaller steps as we move closer to the global minimum. So how do we update this? You take the first each of the weight, you calculate the new weight and store it in temporary one. Then before you update, you calculate for the second one, second weight, you put it in temporary, then you update all at once. So it means that if the number of weights that we have in our network is 1000, you have to have like 8000 temporary storage. Then once you are done with them, then you can now replace with the new values. Notice that we say that if your alpha is too small, it may take an infinite number of time to get to the global minimum. And if it is too large, you may end up actually diverging, and you can overshoot and shoot and shoot until you can not even get back to the global minimum. So that's essentially that. Let's look at it in another material here. Here it says that essentially once we have gotten our error, all we need to do is for us to be able to backpropagate, just like we mentioned. We backpropagate. We have our error, and to find a way to propagate the error, we try to update the what? The weight and the biases. And how much should we update the weight and the biases? We do the derivative with respect to the weight and the biases. The derivative is just a slope. For instance, if we look here, if we take the derivative of this, it tells us the direction we need to move towards the minima, which this is our goal, and this is where we are. By the time we take the slope of this, we move in the negative of the slope. So the weight at the minima of the function minimizes the loss that we want, and that is our goal. We want where the loss is minima. As you can see here, this is where the loss is minima. Here is where the loss is maxima. So the value of the loss function tells us how good our set of weight is. The value here is the best for this. So the weight that corresponds here is the best set of weight. So we can simply update the weight and the biases by either increasing or reducing them once we have the derivative. But we can't directly calculate the derivative with the loss function with respect to the weight, because in our loss function, as you can see in this place, yes, as you can see in this place, you discover that here our loss function might not actually contain the value. Like you can see here, this is our error. This is for linear regression. You can see in this is this error. This is the error that we're trying to. This is our prediction. This is the actual value. So what it's saying here is that the loss function might not contain the weight and the biases that we actually want to optimize. Like here, it's not there. There's no weight or biases here. We only have the input and the y. So So we're going to have what we call the intermediaries between our inputs. We have intermediate variables between our input and the output. So we need to do a chain rule to help us to be able to calculate this. Once we know the slope of the loss function, which is also the error, we can adjust the weight accordingly. That's essentially what the back propagation is. Thank you for listening. Hope this will be very uh, clear to someone out there. Thank you. See you in the next one.